We are in a lecture series on solar power, solar energy forecasting in Thailand, and this is the second chapter that will explain all the elements that should be involved in order to develop a forecasting model. I would like to express the key elements into three areas. The first one is the a platform or the framework to collect the data sets. And certainly these would involve sensor or sensor installation or the equipments in order to acquire all the relevant inputs that we think are necessary for the model. It would come with data acquisition system. And once we get these raw data, the platform that store these data set would have to contain a pipeline of pre-processing. And the as we know that we have to select a relevant input for the model. These also involve the step of feature engineering. Once we get the data, of course, the main focus is to develop a forecasting model. These will require the concept of designing the model architecture. So this is the work of the data scientist, okay? And you can perform the training process and validate the model, tune the hyperparameter, and test the model on the new data set, and prepare the model that will be used in the model inference mode. So a lot of time people develop the model offline based on the batch historical data set. This is quite the common practice. But once you get the model and you're going to use that in practice, so I would say the last step is to implement implementation. You're gonna have a system that um, that contains all the data pipeline, certainly contain the database that store both the it depends on how you design this, because there will be stream data from many sources, depends on your model configuration. Your model could be like, I need more I need input from the sensor. I also need other input variable from outsource, from other services. Okay, so uh so the way you decide this will be quite problem dependent. Mhm. And in order to infer the model, you need all the model functions, all the modules. This is the key element, how to implement it. And certainly, when you calculate the forecast value, your platform will involve how to show the results, and uh, maybe some example of dashboard. And this also require another aspect of skills of how one can simplify the result and present it in the most beneficial way to the users. Okay. So all of these schemes, all of these elements involve many fields, starting from remote sensing, from EE, because the variable that we dealing with the most is the electrical load, right, and solar power, solar irradiance. It also involves atmospheric science, because, as I mentioned previously, that common input variables are from the weather. Okay. So the weather condition that varies a lot is the thing that makes renewable energy variable, unpredictable, and give us a challenge to develop the forecast model. You also need these require skill in the data analytics, and to implement things that make things make make everything practical. We need system engineering and software engineering. Hmm. Let me just give you an illustration of how we have the facilities, how we have infrastructures in our EE department at Jula. For the source of data, we have sensor data, we have a mathematical model that calculate the clear sky irradiance. We also rely on using the weather forecast from NWP. Okay, this figure is a weather station on the rooftop of EE building. So you have this is a sensor of wind speed. I think we have I think it's behind this we have irradiance sensor, and these also have temperature sensor as well. Um, hmm, eh, in other system, all right, for example, for utility or for factory that has solar farm, um, of course, they would have a system, or they might have SCADA system to transfer the data between the equipment and the ground station. Mhm. Um, in For numerical weather prediction, as I mentioned, it's a it has initially it's a global model. It can provide a weather forecast all around the world. But in this model, it also have regional. It also allow you to compute things in region. So typically, as I mentioned that typically these provide as a service globally, and you can either subscribe it to some commercial or uh, third party service to acquire. For example, you can say, please give the temperature and irradiance forecast in Thailand location, which is not here, Thailand location, and they're gonna tell you the resolution in terms of grid, in terms of the spatial resolution, and you can tell them, give me 3-day forecast with the resolution of 30 minutes or something. Okay. Hmm. And I think there are NCEP, there are WRF, okay, there are ECM, this is European something, okay, and other ones, okay, there are many more. Hmm. Time series example of these variable, solar irradiance. The solar irradiance has a daily cycle. At noon, it would be at peak, but it depends on the weather type as well. Sometime during the day, you have cloud coverage. You may have rain. So that's why irradiance drops sometime and fluctuates. UV index. This is some example of the from the NWP model. Um, it may resemble the trend of solar irradiance as well. You see, solar zenith angle is a variable that okay. Suppose we have so suppose this is the sun. Okay, suppose this is the sun. Then we have the vertical, the upright position here, and we can measure the angle here. This is called solar zenith angle, but it typically reports as the cosine theta. So at noon, when the sun is here, the cosine theta is at maximum. And for around 90, which is in the morning or in the afternoon, the solar zenith angle would be 0 and entirely 0 at night. Okay. What else do we have? Relative humidity, that is the unit of percent. So it varies a lot, and this depends on your weather climate. For example, Thailand is a tropical climate. From my experience, we have the range of 60 to 70%. These sometime during the rainy season, the humidity is very high. Wind speed typically offer in made per sec, and also come with the with the direction that gives you in the order of degree. So they might say that I'm not sure about the reference axis, right? But you have north, south, you have east and west. They may develop an acid, and they can say that, oh, the wind speed is in 30 degree, 30 degree with the reference of the this direction. Clear sky index. Okay, let me give you the definition of clear sky index. So K hat is the actual measurement of irradiance divided by the clear sky irradiance. So the clear sky irradiance um, let me just explain this first. So the clear sky irradiance is irradiance value under the clear sky assumption. There's no cloud, there's no particle, there's no mass. So that's why everything is so clear, right? At noon you get a peak, but these values on the different days are not the same. When you look at the mathematical model, the input of clear sky model highly depends on your uh, location, lat long, um, day of year, and depends on time, so that they can. So basically, uh, you need day of year because it gives you the sun path. You know that when we orbit around the sun, right, the position of the sun on different day is different, and we need the time so that we can approximate the position of the sun at the time. So um, that's why the values of these cycles are not exactly the same. Okay. Compare solar irradiance, the actual value, with the clear sky one, right? If you compute the ratio of this guy to this guy, that gives you the clear sky index. And typically you would think that, can you guess the range of K? Hmm. Because typically the clear sky would be higher than the actual irradiance. So I forget to give you the physical range. This would be like 0 to 1,000 something, and depend on your geographical location. In Thailand, I would say in Thailand, I would say not at most it's not more than 1,200. The unit is the watt per square meter. Okay. Um, so the actual irradiance typically less than the clear sky. So when you compute the K clear sky index, so this number is typically less than or equal to 1. So by the name suggests, the higher K is, the clearer sky you have. Okay. This is some example of forecasted irradiance from NW model, where the model name is WRF or WAF. People call it WAF, I'm not sure. So this is also the predicted value. So you may use that. Okay, I have an approximate trend of irradiance for tomorrow. Maybe I can use this thing for as a feature input for your model. The temperature. The temperature typically has a daily cycle and seasonal cycle over months. They may have variation over during the day. In Thailand, in order of Celsius, if it is in Celsius, I would say it depends on your location. Like in Bangkok, I think we have 20 something, like maybe 28 or something, like the minimum range, and we can hit to 40 something. Okay. This is some example in Bangkok. Okay, and of course, for other location in Thailand, in the northern part, the temperature can be lower in some area. Overall, when you see the time series of this thing, you see that a lot of variable has a daily cycle. All right. they have a very unpredictable fluctuations along the time. So we can say that typically these are not stationary at all. And so with this in mind, the patterns are very complex. With this in mind, it means that maybe if you try a simple model and it doesn't work well enough, it means that you have to adjust the model architecture to be more complex, more nonlinear. So talking about the model, let me catch up the background, okay, so that we have in the same, like we're in the same ground. Hmm, if I split the model types into a broad categories, I would say first we say a model is either static or dynamic. Static model means that an instant value of y at a particular time directly depends on x at that time. Okay. For example, y is a quadratic function of x like this. Y is exponential function of x like this. All right. Or this nonlinear function. You see that if the relationship, your model, your representation of y as a function of x, you see from this formula that x at time t give you directly instantaneously the value of y. This is static model. On the other hand, dynamical model means that your your signal y has a temporal dynamics. The value of y at time t not only depends on the current value of x, but also the history of x. The very first mm, uh, dynamical model that that we have seen in our elementary, mathematical class would be ordinary differential equations. This is first order ODE, right? So we all know that when we solve this first ODE, we're gonna have something like YT as a uh, as a as a convolution integral, right? I'm not sure if you follow this, but please review, right? Please review that your solution would depends on two terms: homogeneous solution and particular solution. And for the particular solution, of course, it depends on the signal xt, but this is convolution between your uh, what we call state transition matrix, state transition function with the input x. With this with this expression, we will see that uh, you have to integrate this convolution integral when tau equals 0 to t, and then you get yt. So your yt is a collection of your past input x, your past input, because these tau vary from 0 to t. Okay. Um, of course, first linear order ODE can be extended to any, this is a state space, state equation, but it is nonlinear because generally f can be any nonlinear function. When your model, okay, this is by the aspect of either static or dynamic, but we also have another aspect of considering the model. If your model, if sorry, if your signals are random and you would like to treat it as as random variables, so you can say that I'm going to develop a probabilistic model. I'm going to use somehow statistical information of random entities that involve in your problem. You're going to use that information as well. For example, I mean, I just give you some simple example, like Uh, suppose y of x are random, and somehow from application point of view, your y may take positive integer values. For example, the number of, I don't know, the number of passengers, passengers uh who uh who come to get the service at a counter or something, right? So you can say that, okay, the number of passengers, oh sorry, number of customers, not passenger. If you have a number of customers at as a service, you may think that, okay, maybe Poisson variable is an appropriate distribution. But how can I relate the Poisson model with a certain rate, right? Different rate give you different Poisson distribution. And how can we associate our probabilistic model that could depends on x? In this example, you may say that, oh, the rate of your Poisson process could be a function of x. Okay, so this is some typical example where you let a lambda, which is a rate, to be exponential function because it returns a positive value. Okay. In order to like maybe adjust like some background uh so that you can follow easily, we will use these terms interchangeably all the time. When we say input, it's the same as predictor, features, explanatory variables, independent variables, or I mean I can add one more thing, regressor. So these terms used in statistics, these are used in a feature used in machine learning, right? For the output, which is y, right? Input is the x. For the output, we use response variable, explained variable, dependent variable. In machine learning, people would use the term target of the learning. Mhm. uh, okay. So I think I explained like some details of data model, and now maybe some comments on the ICT on the infrastructure design. um I think there are a lot of details involved and a lot of problems as well, but I think overall I can get that, oh, you need to design the database, all the processing units, all the tasks that need to be done. You have to decide like the structure of the modules to be calculated. Data flow visualization, a lot of issues. Maybe the list will be many more. I just maybe sketch the first two ones that involve the data. Is that the data are not perfect when you experience something in real time, right? This is going to be like realistic problem. You have missing data. Data come with a delay. So even though in the offline version of your study, you say that you must acquire these variable at time t, but in practice, they will come with a delay. Okay. Uh, so when we see like the the key elements that involve in the forecasting, I would like to explain that once we have these tools, once we have data, once we have the model, I mean, there are different approaches, different frameworks we can provide. There are many aspects because there are many aspects of solar forecasting problem. So so these aspects depends on the problem specification and resources. I can make the bullet. I mean, what I'm going to explain is that when we perform forecasting for single site, multi-site, and when we perform on different locations that have different set of available inputs, all right, the framework of implementing this would be different. Let's go over the first one. This is going to be the simplest one that we will start with, because typically the question will be that, okay, I have solar farm in in the eastern part of Thailand. We have the lat long. latitude, longitude, can we have install capacity with the capacity of 2 megawatt, for example, and can you predict the solar power we can generate? Mhm. Like each day, for example. So when we have the problem requirement, remember that, as I mentioned before, the basic requirement is, of course, what horizon, day ahead, or hour ahead, or minute ahead, right? And assume that the model that is responsible for each horizon is different. They're not going to be the same model. What I mean, not different, not the same one, is like you could use the same method. Like for example, I could use LSTM for all forecasting horizons, but the specification inside my module's architecture would be totally different still. Okay. For the single site location, the the necessary inputs, I think I can split them into two categories. The first one is region-wide inputs. This is something which means this is something that we can acquire in a in a wide area, but you just extract the information according to your location. For example, from the satellite, we can see the coverage of cloud, and we know that the cloud influence the solar irradiance, right? Because if there's a cloud cover, the irradiance is less. So it means that whenever you have the satellite, we can get the cloud mount all over Thailand, for example, and you can just extract the one that corresponding to your site, your solar site. We have NWV forecast, the weather forecast that I mentioned that, okay, it provide you a global model. Again, you just subscribe to the coordinate of your interest. Clear sky model, clear sky irradiance, or GHI. Um, this is a mathematical model that end up into maybe a certain lines of coding. So this is something that you can synthesize always at any location, any time of the year. This is region wide. Suppose you have access to these variables. Also, the other one would be the local input, something that you can measure and acquire from at your location. You have installed the sensor of solar irradiance, temperature, humidity, and solar power. And in addition, if you can install the sky imager. So this is like you have a camera that project into the sky just above your solar panel, and you see, and this is to detect the cloud coverage at that location. Okay. um do I say that you have to install all of them? Probably not, and everything would finally, you know at the end, it depends on how much resource you get, and the budget. Okay, if you have capacity to install so many sensors, okay, and you do so, but you can maybe selectively install the variable as well, the sensor as well. I would say that in the context of solar power forecasting, install the solar irradiance and the solar power that automatically come with equipment as well. I mean, these two ones are the main ones, are the main one. But you also you also need a cloud information that highly influence on the variation of irradiance. So it depends if whether you can have the sky imager, or you're gonna rely on the satellite. Okay. And so this is an example of how one can think of a framework in the single site forecasting. For multi-site, okay, now I can say I can have for example, if I am the owner of a solar farm company, I have the solar farm in central Thailand, maybe 5 solar farm in central Thailand, 10 farms in the eastern part, the northeastern part that has a very high potential of producing the solar power. Then how can I set up this system? Okay, I would say that because you have multi-site, right? I also I also uh and this is my opinion, okay? My opinion is that if you have many locations, I would go to indirect approach where I develop irradiance forecasting model first, because this model should be used should explain the physical nature characteristic of the sun. I would develop this universal model, okay? And but in order to develop this model, okay, in order to develop this model, I may have to have access to data sets from many locations so that you can learn the characteristic of irradiance from different latitude and longitude. Okay. What I mean is that this is a model, right? This is a model. I didn't mean that these group are different models. What I mean is that you have a single universal model, but you can execute it in parallel, but that like each of the sorry, each execution of the same model just use different inputs, and that inputs are of course typically different from the lat long location, the different in terms of the weather information at the same time, all right? At the same time, because at the same time, the sun position relative to this location would be different from the sun location relative to this location. Okay, the cloud amount occur at this would be different from the cloud amount at this. So that's why you have the same model, but you have different input, and you get different predicted GHI. I didn't have it in. GHI is global horizon irradiance. It's basically the total irradiance amount you can measure from the ground where you install the solar panel. Once you get the predicted GHI or irradiance at many location, what you're gonna need to have in your system also the PV conversion model. Let me recall. Can you recall that actually I have implemented um eh, where is it? Yeah. Come back to here. I mean, recall that I have two frameworks, right? Indirect approach and direct approach. So what I'm explaining here is that I'm using the indirect approach. I forecast I irradiant first, and then I have different PV conversions model. These are just, I would say, linear model with different multiplicative factors, because different solar site, different solar farms would have different capacities, right? So, so the meaning of this PV conversion model would be the efficiency. How can you convert the GHI, convert the irradiant into solar power? So this keeps the information of solar panel efficiency and the size of your solar farm. And once you have different results, and this is how you can get the solar power at different locations. um, so when you have implement this, I mentioned that I use this as a universal model, right? Which means for the universal model, you have to think very hard, because it means that your model M here would take would take x, like You take the same list of variable for all locations. Suppose there's this location have cloud and have temperature and have irradiance, right? But this location has only temperature and irradiance. If you use universal model, your universal model cannot say that I'm going to take cloud, temp, and I as the input because the other location doesn't have one variable, which is cloud. Okay. So this is quite a drawback of universal model because you have to implement it uniformly in all locations. But it's kind of simple in terms of implementation to run all the models in parallel that require the same set of input. Now, the next one, this is the aspect of like how to implement the model in the aspect of either single site or multi-site. But I would say the aspect that like effectively impact on the decision of how you come up with the model is actually the data availability because the data is the raw ingredient for your model. So when we have this in mind, I would like to I would like to uh design the model according to available inputs that you have. So let's say that we all have a common available input, which is the region-wide inputs, the satellite cloud, the weather forecast from NWP, the clear sky irradiance. Assume that we all have that, okay? So let this is like the fundamental input that everyone have, plus the ground measurement input that each location might not have the same, okay? For those who have the full information, have irradiance, have power, have cloud, IPC. Okay. If everyone has like full information like this, I would, again, this is also my opinion, but yeah, I'll let you decide whether you agree with me or not. I would say I would go to indirect approach where I develop irradiance forecasting model so that I get I had first. But I'm going to use the data set of irradiance and power that I have to develop a PV conversion model, like a linear regression, to calculate this factor so that I can convert irradiance to power. Okay. Okay, this is the first choice. If you fall into this category, you may try this approach. Now, for the second category, if your solar farm doesn't have any ground measurement, ground sensors at all, you didn't install temp sensor, you don't have sky imager, you measure only the solar power. Okay. You may consider the direct approach where you develop the solar power forecasting model that directly gives the forecasted power. So your input, but because forecasted power depends on the irradiance, right? Depends on the irradiance, depends on the temperature, depends on other things. So that's why for the temperature, you're gonna need the information from the weather forecasting service instead, not from the measurement. Okay. And and these depends whether the service that you pick also provide the forecast of irradiance or not. Okay. If it does, it will be great. Okay. Um, Last would be like a very the one with the very limited resource. You don't have measurement of anything. All you have is the information of installed capacity of solar panel. Mhm. So maybe I think um those those who are solar rooftop residential area would fall into this category. Okay. Even though some household may have the information of measure solar power, but I think or we can think of the I think like I'm the one who performed the forecast. Maybe I'm in the role of utilities, but if I'm going to forecast the solar power from household area, I don't have information to the generated power from each house, right? So I would fall into this. Um, what I can think of, like our solution for this is that somehow we have a pre-trained model that developed from another data set, and this is irradiant forecasting model. Okay. And then and then so this is the forecast of irradiance. And this actually this block is a model that is now available from many commercial services globally. Now you can like Google the solar power, solar energy forecasting service, like there are some names, right? Um Solargis, um uh oh, like somehow I just lost the word. Eh, eh, Soulcast. Yeah, I'm not sure if I remember the name correctly, but I mean there are many ones out there. All right, they have somehow have a collection of big data sets, and so they develop this model. But how can they know that? How can they know the power generated in your exact location? You're gonna need these plant factor. S- Okay, so you need to supply the information of your solar panel capacity size, 8 gigawatt, all right? You have to maybe additionally you give them the tilt angle, how tilt your solar panel from the reference axis. You may give the information of the install date so that we can calculate the degradation factor, right? So this is going to be a very rough estimate, I would say. If you don't need if you don't know anything about the measurements, all you need to do is this is basically to estimate the solar panel efficiency and the solar side according to your install capacity, so that we can get a multiplicative factor to convert irradiant to forecasted power. Okay. So yeah, uh you have to like maybe concerned with the data availability before developing a model. Eh, Let me give a little more detail about the PV conversion. All right, if you have full access to solar power and solar irradiance data sets. Okay. We use P for solar power, we use I for solar irradiance. And now in this graph, I make a scatter plot between irradiant, which is kilowatt per meter square, and solar power in kilowatt. Let's say that I have three data set from three solar plants. These solar plants have different installed capacity. Um, you can see that both P and I exhibits a linear relationship. Very clear, very clear. And from here, we can use the symbol model P equals alpha I linear regression. And hypothetically, you could say that the cell or the module temperature, the temperature that you just measure like underneath the solar panel, and that also affect the efficiency of the panel as well. So you may include this cell temperature in the model if you have access to this sensor, this data. Okay. Um. So, but let me just get back to the symbol one. If P equals alpha I, what P equals alpha I is kilowatt per meter square. P is in kilowatt. So the unit of alpha would be certainly square meter, right? So the slope of this guy keeps the information of how big is your solar system, solar panel is. But it also implicitly keeps the information of panel efficiency. So, like loosely speaking, I say that slope, not, I mean, this is not like directly additive. I mean, conceptually, the slope contain the information of panel efficiency and the area. Within the same plan, if you collect this data set 10 years later, okay, how would you think if you plot the scatter plot again, how the scatter plot would change in relative to these red plots? Should it lie above or should it lie below, given the same location? 10 years later, solar panel should be degraded, right? So when you make the scatter plot 10 years later, it should lie below. So that's why I say that efficiency is hidden in this scatter plot information. Okay. Okay. I can also, what if I scale the solar power, I normalize it, all right? We can say I normalize it. Uh, P TUD is P divided by install capacity, right? So now it unitless. Okay. So if I do that and I make a scatter plot again now between P TUD or the normalized P and I, you will see that the scatter plot from the three location now they tend to align more closely because now you get rid of the differences in the capacity of the system. Now the information that are kept in the slope is the panel efficiency. Okay. And of course, the panel efficiency differs from each type of the solar panel, each manufacturer, and depends on its period of using the panel. I make a one note here that when you also in summary, my message is that in when you want to compute this, you train and you want to develop PV conversion, you can use information of P and I and develop a linear regression model as simple as that. But with a note that the solar efficiency can vary over time. So um you may need to use recently obtained data set so that the issues of solar panel has been degraded has get rid of. Yeah. So another method that I would like to explain is that when you have to make a decision between deterministic and probabilistic forecasting, what would be the main different tasks or different list to do? Okay, this is the two types of forecasting model have different targets. So I would say that these impact on the training process. These impacts even on the process of thinking about model architecture. Okay. So I have these two tables. We have deterministic model and probabilistic model. For the deterministic model, your target, your output of variable is actually that variable to be forecasted. If you forecast solar power for deterministic, that Y is solar power. If you have electrical load forecasting model, that variable is the electrical load. For probabilistic model, if your model release the prediction interval, right? That is the prediction interval of your variable of interest. if your probabilistic model release the quantiles, so it's going to be the quantiles of that variable. I hope you following this. Like if I develop solar irradiance forecasting model, deterministic approach, the target would be I. Probabilistic approach would be the prediction interval of I, quantiles of variable I. Okay. As you will see that when you develop a model, it requires the training process, and your model parameter will be updated in the training process in a way that that satisfy the objective of training. That objective of training is usually specified by the training objective or the loss function. So typical loss function for deterministic forecasting would be mean absolute error, or MAE, mean square error. In robust regression, people may use robust loss like Huber, and I think there are many more. All right, so we can check out these information from statistical learning papers. For probabilistic, the training objective would be different. Um, Let me just explain things like if you have the data set, right, and you have to develop a PI, mhm, a PI prediction interval. What you need is that certainly a PI should cover your actual value. All right. So it means that one of the training laws should be the coverage probability. If your PI is guaranteed at probability 0.9, when your model should be trained um, in the sense that the PI that produced by the model should cover the actual values with the probability of 0.9 that you set. Mhm. Another aspect of a good quality of the PI also is concerned with the width. The width is the height, all right? Yeah, the width is basically the upper bound minus the lower bound, all right? You need the PI width that is small because certainly if you look at the coverage probability alone is not the only metric you should concern. So you have green PI and you have the blue PI. Both PIs can cover most of your actual values, but the blue PI is so much wider. Is it good or is it bad to have a wider width? You guarantee something with the same probability, but your guarantee region is much wider. So your information has more uncertainty than this one. So that's why typically the PI width is preferred by the narrow width. You can also integrate these need in order in the training loss so that your PI behaves that way. If your probabilistic model release the quantiles, it is known in statistics that an appropriate loss function is the pinball. So pinball loss function has a meaning that if you use this pinball loss function, the quantile that projects uh, the quantile that I mean the output of the model is um is fit to be the sample quantiles of your variable. I can explain more when we talk about the technical detail of forecasting model. Sorry. This is a diagram of how to define the model architecture for each of the two framework. For deterministic model, your target is the point forecast. Probabilistic model, it depends on how you how you determine or you define. It can be quantiles or it can be upper bound, lower bound of the prediction interval. Or your probabilistic model could provide both prediction interval and the point forecast, like all in combo. Okay. So from these two, I use variable x and y like only in a in a general notation, like just x and y. But if I need to, I need to make a very specific notation for the context of forecasting model. Because for the forecasting model, we going to predict something in the future. So let me use the notation that we're gonna like execute this model at time t, at time t. So the input that you're gonna like feed it into the model would be anything, any variable that you think is appropriate to explain the target, but it must be available at time t. And what you're going to do is that you're gonna forecast the values at time t plus 1, t plus 2, t plus h, where h is your horizon. Okay, so I use this notation. This is the discrete time indices. So typically, forecasting problem is it has like your model has multi-step forecast output. Your output is a vector. So this is this is an example of prediction interval estimation. Okay, so you have different colors. It means that your prediction interval are obtained from different methods. You can see that, for example, um, around this area, the green method gives you a wider width, which is not which is less favorable, right? While the blue model give you a narrow width. Okay, so this is the benefit of each method that is not the same. Mhm. Hmm. Okay. Um. Hmm. So I think I'm gonna stop here again. Okay, before we uh now what I have explained is how we look at the forecasting problem and how to come up with a framework that differs by the requirement. Those requirements are whether it's single side or multiple side, whether it's deterministic or probabilistic, and whether and depends on how much information you use you could have as the input. So in the next video, in the next chapter, we will talk about we go deeper into the statistical learning methods into developing the model. Okay, so I think we stop now for this video. Uh,